Second half of our lesson. So we've figured out so far that our reactions for redox are always going to be opposites. Something's always going to be reduced and gain electrons. And for those electrons to be gained, they had to be transferred from somewhere. So something else must have lost those electrons and been oxidized. So we've definitely focused on that one half is always going to be reduced and the other half is going to be oxidized, but we haven't quite looked at the electrons specifically and how many electrons will be transferring. So that's what we're going to look at in half reactions. So yes, we've got a balance so far by looking at gain versus loss always in redox reactions, but we always want to make sure we have an equal number of electrons being lost as we have being gained. So that's what we see in our half reactions. So it's just a little extra step onto what we've already been doing. So in our assignment, the second page has 4 questions that go just like this. So I've tried to do the next 2 questions exactly in that manner so that you can pretty much replicate them for your assignment. So here's the first one. I just took out the title and I put a reaction up here. So here's our reaction. We've got copper chloride mixing with solid calcium, and on the other side we've displaced the copper and it's now solid, and calcium is now bonded up with the chlorine. So I've just rewritten it down here, and we're going to go through some steps that will seem repetitive from before, where we're going to break it down into the total ionic and net ionic reactions, and then we'll look a little bit more on what a half reaction really is. So nothing new for numbers 1 and 2. Total ionic, I've taken copper and the chlorine and split it into its atoms. So copper, we're going to choose 2+ because that 2 behind the chlorine came from copper. So we've got a copper 2+. We've got to make sure that 2 gets counted though for the chlorine. So we've got 2 chlorines, 1- always. Calcium, nothing too difficult. Let's just add a 0 because it's all on its own. And we'll have to break this one apart too, right? So calcium, that's where the 2 came from, or we can look at our periodic table. So it's a calcium 2+. Chlorine looks like it did on the opposite side. And copper all on its own, so let's just give it a little 0 because it's neutral all on its own. So I took the time, I decided to stroke out my chlorines on either side because nothing changed with them, right? To write my net ionic equation. Everything else that still remains had some change though, right? I've connected them by arrows, where I've got my copper 2+ becoming a copper 0, and a calcium 0 becoming a calcium 2+. So if we look at copper first, we went from a 2+ to a 0. So if we're going down in charge, we gained something negative, those things being electrons, and we know that's reduction. So it's been reduced, or we can call copper 2+ an oxidizing agent. The opposite is true for calcium. We've gone from a 0 to a 2+. We're going up in charge, which means we lost something negative. We lost electrons. So this guy's oxidized and it's a reducing agent. So that's kind of where we left things before. What we want to do is this extra step. We call it a half reaction. So half reactions, we have 2 separate reactions. Both of them together would make the whole reaction, if you would. So half reactions actually make us physically write out how these electrons are being transferred. And another thing to point out in half reactions is that the number of electrons you have in either one of these electrons has to be the same. So before we actually talk about why these are here, we have 2 electrons in both of them. As well, we have electrons on the reactant side, or the left side in one, and electrons on the product side, or the right-hand side in the other. So always the same number, and always on opposite sides of the reaction. One's going to have to be a reactant, and one's going to have to be a product. So figuring out how many we need and where they go is just the last step. So if you want, the easiest way would be to first write in what I have in black. So you know we started with copper 2+, so that's going to be in this half reaction. And we ended with copper 0, so that's going to be the other side, and we'd figure out the electrons after. Same thing for calciums. So we knew we started with calcium 0, ended up with calcium 2+. Let's write those down and we'll figure out the stuff in the purple after. So we can look at charges, which is what I've kind of been drawing so far in the pink. So we've got 2+ going to 0. We're going down in charge by 2, right? We're going up in charge by 2. So those charge differences are the number of electrons we're dealing with. So we know we're going to be dealing with 2 electrons. We just have to figure out now where those 2 electrons will be placed. So that has to do with these terms, loss and gain. So if you're gaining electrons, a gain is going to be on the reactant side. So gaining electrons, if you're being reduced, it's always going to be on the reactant or the left-hand side. That's in your assignment. And if you are losing electrons, they're going to be spat out the other side as a product. So if you're being oxidized, your electrons are always going to be on the right-hand side as a product. So reducing, going to be on the left-hand side. Oxidizing, going to be on the right-hand side, and always an equal number. If you come out the end and you find out you didn't write an equal number, it probably has something to do with balancing. So we'll see that in the next one. Because this guy has balancing involved, right? We've got it pre-balanced, and the ones in your assignment are actually pre-balanced too, so that's nice. So we've got 2 solid aluminums mixing with 3 of the zinc nitrates, going to 2 of the aluminum nitrates and 3 zincs. Okay, so once you see some numbers, it gives it a little more difficulty, but nothing too crazy. So just make sure you don't drop any of these numbers when you go to the total ionic. Make sure you do a double check when you do it. So we've got 2 aluminums. We've got 3 zincs. As you can see, this is where I screwed up. That's why I just had a weird pause. We should technically have 6 nitrates here, right? Because we've got the 2 times the 3. We should have 6 nitrates. We've got 2 aluminums. Again, 6 nitrates. So that should be a 6. That's on me. And 3 zincs with a 0 because it's all on its own. The nice thing about that error is that our nitrates are obviously going to be our spectator ions. So my error actually just got completely taken out and we're back to a correct net ionic equation. That worked out nicely. If it wasn't a spectator ion that ended up being balanced incorrectly, you'd probably notice it about here. I'm going to pretend I did that on purpose. So, okay, cool. I've connected everything. We've got an aluminum 0 becoming an aluminum 3+, and we've got zinc 2+ becoming zinc 0. The thing is, we've got numbers in front of everything, right? So if I look at aluminum, that's where my brackets are coming in. We're starting at 0 and we're ending at 3+. I put those in brackets, right? But I've got 2 zeros becoming 2 3+. So I've ended up multiplying those out. I've got 2 times 0, so obviously that's still a 0, and 2 times 3, 6. So I've gone up in charge by 6. I've lost electrons to go up in charge. I've lost 6 electrons to go up in charge by 6, right? And so if I've lost electrons, I've been oxidized, or in other words, aluminum is the reducing agent. Let's just definitely double check our answers because once you're dealing with like kind of some algebra, it makes things a little more difficult. So we've got 3 2+, okay, becoming 3 zeros. I'm going to just multiply it out. 6 going to 0. Cool. So to go down in charge, we must have gained electrons, gained 6 electrons more specifically. So we've been reduced, or we can call zinc 2+ the oxidizing agent. So how do we put that into half reactions, which is our final step? Sure, we can just draw the stuff in black first, because we definitely know that, and then add in our electrons afterwards. So it can be one of those things where maybe you sense a trend instead of problem solving it every time. And it's the first 2 questions on your assignment too, where if you are being reduced, you're gaining electrons, right? Which means you are going to have electrons on the reactant side, the left-hand side. And if you're being oxidized, you're losing electrons. So you're going to have your electrons as a product on the right-hand side. So you can kind of remember it in that way and justify where you put them. Or the other way would be to look at your charges. So you've got a 0 charge here and a +3 charge here. So if you add some negative stuff here, your charges would end up balancing out because this would be net charge of +6, and that would balance it out with a +-6 to be the same as a 0. Same thing here, 3 times 2 plus would be a +6. If you're adding -6, you'd have a total net charge of 0, which would be equivalent to this 0 over here. So either way, if you're a numbers person, feel free to balance with charges that way. If it's just easier for you to remember that reduction means you're gaining electrons and therefore it's going to be a reactant, and oxidation means you're losing your electrons, so it's going to be a product, just make sure they're opposite. And again, make sure they're the same number. So if we have 6 electrons being lost, we need to have 6 electrons being gained. So just one extra point that we have to talk about before we're done is that so far we've only looked at metals and we've been able to break things down into their ions. But we can actually have redox occur even with molecular compounds, so things that are all non-metals. So we can't actually break those down into ions though and write an actual total ionic or net ionic reaction. Instead, what we can do is we can assign them an apparent charge in its place, and that's called an oxidation number.